Hi, I am here to give a short introduction on the online course of Applied Physics and Basic Principles of Sonography. You have to have a strong foundation uh, on basics of ultrasound for the best practice of sonography. This course helps you to achieve that through 10 lecture videos of about 6 hours duration, which can be listened to at any time, at any place, and any number of times with any number of breaks for a period of about 30 days. It starts with a description of the applied physics essential for physicians, which is explained through plenty of illustrations. And then it goes on to uh, uh, orientation of the image, and then uh, to the movement of the probe on the patient. The next lecture is optimization of the image using the various knobs available on the machine. And then it goes on to the physics of spectral and color Doppler. There are various effects of propagation of ultrasound through tissues, which can be useful signs or artifacts, which are explained again with plenty of illustrations. The last segment is the most useful tips based on some basic principles of sonography, which are usually ignored and which are essential and to be kept in mind during performing the sonography, and modify the technique to achieve the best diagnosis. Here follows the snippets of all the topics in the lecture videos. Please go through them, and if you wish to subscribe, click on the training on www.sonoshare.in and enjoy the course.
So this is called the pulse echo technique. In the grayscale imaging, what is altered in the incident beam? What is altered is the strength of the ultrasound pulse, how much of the incident beam is going to come back as echo. So that depends, that is determined by the difference in acoustic. It is 0.004. The average human tissue is 1.6, and for bone it is 7 of the eyeball. So this is A mode. Then we come to the B mode. B stands for brightness. Human body. When you do the compound B mode, you see the person riding the horse. Because the frame rates are less, you see each frame is changing. So this is form image. So how can you do that? So suppose you, so how this happens? So the explanation for the attenuation. So this is along the line of the beam can be shown as two different structures. So that is the ability of the machine to, so which part of the patient comes where on the image. So without scan, and with a scan you see the transducer skin interface. So this is the transducer skin interface. This is the foot mark. So this will be head end. So here again this will be head end. Opposite will be foot end. Okay, so now here right and left. So probe mark is to be placed on the right side, right end. So for this, from when you change from sagittal to transverse, you have to rotate the sagittal plane, sliding movement in the lower abdomen in a gravid uterus. So this is the movement done to scan the uterus from fundus to the cervix. One example. And second is you see the from the fetal orbits from to the profile. So that movement. So starting with the orbits transverse and then rotate the probe to get the profile, starting from neck to the fundus. So that we are sure that we have scanned the normal liver contains innumerable echoes. So because of the echoes, imagine that 10% of the beam is the bone and calcification impedance is 7.8. That is the calculus. So the 7.8. So the difference is very high. Again, we have pitch of the whistle becomes lower. So the frequency has decreased because the wave is rarefied. So the difference between the baseline frequency and the lower frequency is the X. So that is static interface. The echo, we get an echo back, and that echo is of the same wavelength or same frequency as the incident. What happens? Beam. The wave gets compressed. So as a result, the wavelength decreases. So now the wavelength is 0.00. So RBCs are the reflectors which move towards both the source and receiver. Here in the probe, the ultrasound probe is the source as well as the receiver frequency. So it is a negative shift. So here you see the probe which acts as both source and receiver. So the probe reflected wave is higher in frequency. Wavelength decreases, so higher in frequency. So if the angle is 0 degrees, so equation. So what that is the Doppler shift equation. So here what is the FD? It is the opposite direction, negative Doppler shift. Blue the cold colors are given. So this is how the color display happens. Artery is at the knee, it changes course. So as a result, the flow is towards the transducer in this part of, this is the number of 3000. So I have increased the PRF to 3000. So the aliasing gets corrected. So it shows to give an angle to the blood flow direction. Then the frame rate. So the frame rate is the number of frames we are studying. Put the color box, you get all the information. Of aliasing indicates stenosis. So flow character we get in a vessel, because there is movement of RBCs here, we get a flow as a curve. It is like so the velocity information is known, and the last information we get is the nature of flow. So that is assessed by this line, the spectral line. They want to cross, goat will not be allowed to this side of the fence. When you use a selectively use a high wall filter of, okay, so this is for the artery. Whereas for the vein, we don't, we need not be measured is 73 centimeters per second. Whereas if you don't use the angle correction, if you have not ups, the vessel walls come back to its original size. So when it comes back, you see a multiphasic. It has become, angle correction has to be mandatory in these situations. So in obstetric practice, so we get information about distal vasculature. Same thing we get in dampened flow in a distal to spectral broadening. We will see that a little later. And there is also increase in the peak systolic velocity. So then we diagnose stenosis of 70 to 90 stenosis, proximal to stenosis. So we get information about the distal vasculature. It is for when you increase the depth, the frame rate falls to 13, whereas here it is 27, because of the higher frame rate, better resolution and better below this in the plasma panel, and by rotating or toggling you will get adjust the speed to show more number of cycles. So there is wall filter adjustment in the spectral Doppler. This is again a very correction here, and the knob here below you can use to adjust the angle correction. So this is the angle. So as a result, the signs and artifacts are produced by these simplifying assumptions made by the machine, which is not correct, but it is necessary, and acoustic properties of the tissues and physical character. What does that mean? That means deep to the lesion, the organ is more echogenic than the adjacent organ. lesion which contains fluid, whereas by the side, the organ by the side, the beam would have reduced. For a solid mass, there is no enhancement. So it is solid. But here, again, it's an echogenic mass, but there is dense enhancement. That means there is fluid in this lesion. Transducer and then reaches the strong interface, again reflected back. So after 6x time, it comes back. So it multiple appearances of this reflector down. So that results in edge or critical angle artifact, which is due to the critical angle of insonation. So here you see, suppose this is the head, the beam travels straight 90 degrees. It passes, reflector is at an angle. So part of the beam is sent reflected, part of the beam gets refracted. So it is not as bright as dropout angle of incidence. So you make the beam perpendicular to the interface which you are interested. The beam travels directly to and from the echo producing interfaces, and the beam is only single. It assumes that the machine is assumed that the beam is only single, but the propagation velocity is different for liver as different for fat. So that is the machine does not know. It assumes it is the same in both. Because of that, this artifact is produced. The diaphragm is discontinuous. So we know that the propagation velocity, it looks as though, because the beam has a width. Now this is the trans beam. So this is the transducer. We will make mistakes. So artifacts can happen even in color Doppler. So one of the common artifact is 33.7. So this is within the Nyquist limit. Doppler shift, so it is a black. So there will be, when there is a flow reversal, there will be a black line in between. This is due to the 90 degrees. So when the angle is 90 degrees in structures, so as a result you get color in the surrounding structures. That is a phenomenon. So deep to calculus, it is twinkle. So we can recognize that what we are going to cover is the basic principles. You can take it as tips and tricks for best practice of ultrasound. Yes. So if you use a high frequency, what happens? The probe footprint. The probes have a footprint, that is the footprint pointed compression. This is the major advantage of this probe. You can apply a pointed compression so that you displace the gas cross section at this level, and you see that it is not calculus. It is actually the gas in the duodenum, adjacent duodenum or colon, which is causing the artifact. That due to this, is it not seen well? Because what we are interested is the upper margin of the upper lip. So here you see the this part of the tibia is parallel to the beam. So when it is parallel, like the dropout artifact particular to the beam into the particular angle. So this part of the tibia, I have made it perpendicular to the beam, so it is seen well. That is like the angle of incidence is 90 degrees. You don't get any Doppler shift, so you will not see any color filling. That is why we don't get. So how to see in color? You go to the lateral approach again, because of the adjacent echo poor ascites and also appendages seen very well when there is a contrast of ascitic fluid. Meningocele is seen because of the contrast of the amniotic fluid. Here it is not seen because the contrast of amniotic fluid is not there. So the meningocele sac is close to the structure will be better visualized because of a acoustic window, avoiding ribs, avoiding gas, etc. Or the angle of insonation may be perfect in a particular approach. Practically, theoretically shown because of the spine here, we cannot take the pancreas from posterior aspect. Okay, but if you do, the image will look like this. Okay, but this can be done in a fetus. I'll show you how. So where is this applied? I told you one application. Second application is in the fetal echo. So in fetal echo, do the scan from the right flank. Then you see this is right, left, and you see gas is anterior. So with shadowing, fluid is posterior with enhancement. What I have done is I have done a coronal scan from the flank. Why? Because the gas will be going to the non-dependent part, that is anterior part of the, because of the direction from left to right, so it is red towards the transducer, whereas here it is from right to, left to right. This is left to right with the spine here. So as a result, the flow is towards the transducer. So how is this possible? The same structure, how it is appearing red, here it is blue. That depends on the direction we know. Any vessel, if there is no flow, you must think of this point, that if it, what you get red in the pulmonary artery, because the pulmonary artery is at an angle of 75 degrees. Here the spine is posterior. If you make the spine anterior, then the flow is going to be towards the transducer. So main pulmonary artery and both branches will appear red. Okay, is it clear? So the same shown here, but if you make it a lateral approach, what happens? The pulmonary artery is blue because it is away from the transducer. Then the right branch is red because it is flow from the bifurcation towards. We have seen the branches from lateral approach, the branches appearing in different colors. But here you see both the branches are in same color, red. So this is left, this is right. So how can both the branches appear left in longitudinal breech presentation? Then the flow becomes blue because again this is left, this is right. So the flow is from left to right. Here also left to right, but it is towards the transducer. It will happen when there is, these are venous tributaries, both go and join the main vein and flow is. So this is right pulmonary vein blue, left pulmonary vein red. Okay, they join. So here with two colors in fetal echo. So how does it happen? Now this is example, this will become perpendicular. So you will see that there are two vessels. If it is compressed, you see the interface between them in both these. So the confluent vein ascends up by the side of the left SVC and joins somewhere in the root of the neck, the upper part. So when you make a sweep, joins the vein. So this is AV fistula. So this explanation of the color Doppler physics helps us to make this diagnose, solve rare situations like the TAPVC, confluent vein ascending up by the side of left SVC and joining it, which is very rare. Okay, so but this